Hello and namaste everyone. Welcome to week 4 of this NPTEL course on stochastic approximation. So let's do a quick recap of what we have done through these 3 weeks. In the first week we went over some basics of stochastic approximation. In the second week we went over some fundamentals of probability theory. In particular we looked at this concept called as conditional probability, right? And in the third week we used these basic concepts to discuss martingales and also martingale differences, and also talk about sufficient conditions under which martingale sequence converges, right. So that was in some sense one half of the background that we need to understand stochastic approximation. The other half that we need is that of differential equations, in particular ordinary differential equations, whose basics we will cover during this 4th week, right. So in lecture 16 we will sort of give an overview of ordinary differential equations, which in short we will abbreviate as ODE, right. And in subsequent weeks we will see how the combination of ideas from ordinary differential equations and this martingale difference can be combined to understand the behavior of stochastic approximation algorithms, right. So what is an ODE? An ODE is an equation of this form, right, where on the left hand side you have the derivative of a time dependent function x of t, right, and on the right hand side you have h of x of t. And throughout this discussion we will presume that h is a function which takes as input something in the RD space and spits out something again in the RD space, right. So what is the intuitive interpretation of an equation like this? Well, if you think of x of t as denoting the position of some particle and x dot of t as denoting the velocity of this particle, then this ordinary differential equation specifies how the velocity of this particle is dependent on its position. Is that okay? So that is what an ODE is all about. And one can then ask, if you have an equation like x square equals 4, what is its solution? In the same way, an equation of this form, right, we can ask what is the solution to this equation, right. More specifically we can define something called as an initial value problem, right. In this initial value problem we have this ODE x dot of t equals h of x of t, right, and in addition to that we have an initial condition such of the following form, that we have some t naught in R, that is the real line, and we have been given this additional condition that x of t naught equals x naught. So the initial value problem is basically a ordinary differential equation along with an initial condition of the form which includes a time and the value that your solution trajectory should satisfy at that time instance, right. So now one can ask, what is a solution to an initial value problem? Well, a solution to an initial value problem, as I said, is a trajectory, means it is a function whose domain is a subset of the real line, and in some sense this domain represents the time instances, you can think of that, and the output of this trajectory is actually an element in RD. Sorry, there is a typo here, so this should be RD, okay. So what is a solution to an IVP or an initial value problem? It is a trajectory which takes as input something in the real line and spits out something in RD, right, and typically we will assume that this I is a connected interval which is a subset of R, and also it includes this time instance t naught that has been given to us as part of this initialization condition that has been specified, right. So in other words, we have to, if you go back to that position velocity relation, right, the solution to an IVP is basically a trajectory followed by a particle, right, which satisfies that relation for every t in I. Is that okay? And in addition, Okay, it satisfies this initial condition, that is at the specific time instance t naught the solution trajectory should indeed pass through x naught, right. So whenever you have seen an equation of the form x square equals 4 or something like that, one can ask when would such an equation have a solution, and furthermore we often ask, does this equation also have a unique solution whenever the solution exists. So in the same way one can ask what are the conditions that guarantee the existence and uniqueness of solutions to an IVP, right. So we will now discuss one sufficient condition for the existence and uniqueness of solutions to this initial value problem, right. And for that we need to introduce a few notation. The first among this is this set, right. So for any interval I which is a subset of R, we will use this notation which is Ci comma Rd, right, to denote the set of all continuous functions which go from I to Rd. So notice that this I is from here and this Rd is over here. So basically this set consists of all continuous functions whose domain is I and the range is Rd. Okay, so this is what this notation means. Separately we will say a function h which goes from Rd to Rd is Lipschitz continuous. So we will say such a function is Lipschitz continuous if there exists a non-negative constant L such that the following condition holds. So what does this condition say? It says that the distance between the output at x and y under this function h. So h is your given function, so you look at h of x and you look at h of y, right, and you look at the distance between them. So at this point I have not specified what metric is, but you can choose whatever metric you like, for example the Euclidean metric, right. So you look at the distance between them and we will say this function h is Lipschitz continuous if this distance is upper bounded by L times the distance between x and y, right, and this relationship should be true for all xy in Rd. So let me again summarize. A function h is Lipschitz continuous if there is a constant L greater than equal to 0 such that the distance between the outputs is upper bounded by L times the distance between the inputs, and this should hold for all xy in Rd, and this L should be independent of this choice of x and y. In that sense it is a universal constant, right. So with these notations in place, let us now discuss a sufficient condition for existence and uniqueness of solutions to an IVP, okay, and that is stated as part of this theorem. So the theorem reads as follows: suppose the function h, right, which is the driving function in your IVP, suppose this function h is Lipschitz continuous, right, then the claim is that the initial value problem which is given over here. So recall that the initial value problem has two parts. It first has the ODE relation and the second is that it has some initialization condition. It requires that the solution trajectory that you identify at time t naught should pass through x naught. So this theorem says that if h is Lipschitz continuous, then the initial value problem indeed has a unique solution. So notice what this theorem is saying. On the one hand it says that there is a solution, and on the other hand it is insisting that this solution is unique, right. So as I told you, recall what a solution means. A solution means a function which specifies at a given time instance where this particle is supposed to be located, okay. So this is the mapping from time to a value in Rd, right, and this theorem is insisting that if your h is Lipschitz continuous, you will be able to find a unique map which satisfies these two conditions simultaneously. And the second half of this theorem says that the map between x naught to x is continuous. So let us try to understand what is this result trying to say. So x naught over here is the initial condition, right. So for every initial condition, okay, the first half of the result says that there exists a unique solution. So you take that solution, okay, which satisfies the initial condition x naught and come up with this mapping. So every initial condition will be mapped to some trajectory, right, and this first of the theorem says that this trajectory actually is an element of CR comma RD, right. So if you recall the notation from the previous page or previous slide, here we had I, right, and the theorem basically says that you have a solution trajectory which exists for every time in the real line. Okay. So the second half of the result says that the mapping between x0 and this solution trajectory is continuous, right. So we will keep what continuous means and so on and so forth for discussion in the next class. In today's class we will focus on proving the first half of this theorem. So let us see how does this theorem go about. Okay. So to begin with, we are going to define a function f, right, and we are going to first prefix or fix a value of t, right, and let us focus on this set. Okay. So this set is the set of continuous functions which maps time instance which lies between 0 and capital T to a value in Rd. So this is the collection of all such functions. This is similarly the same collection of functions which map a time instance in 0 to T to Rd, right, and now we are going to define a function which takes a trajectory here to a trajectory here. Is this okay? So this is this function, and the way this function is defined is given over here. So you give me some y from this space, f of y will give you another trajectory which lies over here, where at the tth instance z of t satisfies this relation over here. Okay, so there is a typo, let me correct this. This actually should be y of s here, okay, not x of s. Okay. So whatever is the input trajectory, right, you put it over here, take h of that, integrate it from 0 to t, this t and this t are the same, okay, add it to x0 which is the initialization condition that has been given to you, and whatever is the output you assign the value z of t to that. So in this way you define z of t for all t which is there between 0 and capital T, right. So in this way you have this z of t trajectory defined. So I hope you can see that if I give you any continuous trajectory that lies in this set, okay, you can use this f to construct an output trajectory which lies over here in the following sense, right. And also observe that from the because this is continuous, right, from the fundamental theorem of calculus, one can immediately see that not only is z of t a continuous function of time, it is also differentiable. Is this okay? So now let us see how is this relation or this definition of f related to the question that we had, which is that of solution to an IVP. So one can see that a solution x, right, or a x which lies in this map C 0t comma Rd, right. So this is a solution of the initial value problem in this interval. Okay, so this interval, let me write it cleanly, it is 0t. Okay. So in this interval your x is a solution trajectory if and only if x is a fixed point of f. So what do I mean by that? You give x as input over here and the output should also be x. So fixed point basically means that your f of x should be x. In other words, your x of t should equal x naught plus integral t naught, sorry, integral to t h of x of s ds. Okay, and I forgot to mention over here, right, for simplicity we will consider your t naught to be 0. Okay, so this is just for simplicity, but the same ideas will go through even if you had a general x naught. So in this sense you can see that you have x on the left hand side and x on the right hand side, and from this perspective you can see that your x actually satisfies this fixed point relation. Hence if you can somehow show that f has a fixed point, right, then one can conclude that indeed the initial value problem that we had that is given to us has a solution on the interval 0 to t, right. So if you recall in that problem statement, the conclusion was that we will have a solution trajectory over the entire real line. Okay, so we will at this point focus on only having a solution between the interval 0 to t, and later on we will see how to extend this solution trajectory beyond this interval 0 to t. Is this okay? So what is the summary so far? We have defined this function f over here, and the conclusion is that the initial value problem has a solution if and only if f has a unique fixed point, right. Let me repeat, the initial value problem has a unique solution if and only if f has a unique fixed point. So now what we are going to do is we are going to identify a condition under which this function f has a unique fixed point. Towards that, what we will do is we will first define this norm over here, right. So what is this norm? This norm, okay, takes two elements y and z in this set, right, and says that the distance between these two trajectories is the supremum of the distance between y of t and z of t. So recall that y and z take a time instance and spit out an element in Rd. So y of t is an element in Rd, z of t is an element in Rd. So y of t minus z of t are two d-dimensional vectors. We compute their difference, and this norm is your norm of choice, okay, in the d-dimensional space. For example, this could be the Euclidean norm, right. So you take this distance and take the supremum over little t in 0 to capital T. So whatever is the supremum, this will be some real number, that number you assign to the value of this metric. So the idea is that you take y and z, which are two solutions, I shouldn't say solutions, two trajectories, right, and you look at the difference between their values at time t, and look at the value of or the norm of that vector, right, and you take the supremum of that norm, whatever is the answer, that is this definition of this norm, right. So now let us use this definition to see how far is f of y from f of z, right. So f of y minus f of z is, there is some x naught plus something, and f of z will also have some x naught plus something. Because x naught are common to each other, they will cancel off, and we will be left with some expression like this. Okay, so let us just do it carefully. So what is your f of y? F of y is, in particular, f of y at time instance t is basically x naught plus integral 0 to t h of y of s ds. Similarly, your f z of t is actually equal to x naught plus integral 0 to t h of z of s ds. So if you take their difference, I hope you agree that you will end up with f of y of t minus f of z at t, right. This norm is basically less than norm of integral 0 to t, okay, h of y of s minus h of z of s ds, and then I would have this norm over here, right. Now observe what I have done over here. On the left hand side we have this metric with regards to this time instance capital T, which is defined in this sense. So you will have a supremum taken over all these values, right, and by properties of this metric and integrals, one can take this inside via what is called as the triangle inequality. So one can take this inside, right, and this is what you end up with, right, and then because of this supremum you will end up with this supremum over here, and this is how you get this relation, right. So in other words, f of y minus f of z, these are two trajectories in C0t Rd. So the distance between them, right, in this sense is upper bounded by this expression. Now we know that this function h is actually Lipschitz continuous. Because it's Lipschitz continuous, we can pull out this L over here and we would be left with the distance between y of s and z of s, right. Now this expression is upper bounded by this expression is upper bounded by y minus z subscript t, right, because this expression is the supremum. So if you look at the distance at any s, this must be upper bounded by this, right. So we can take this expression, now this does not depend on s, so we can pull it outside the integral, and once you take the supremum you will end up with this capital T, and this is the upper bound that you will end up with. Okay. So now what do we have? You give me two trajectories, right, then the distance between the outputs is upper bounded by LT times the distance between the inputs. That is the summary of this calculation, right. So now what we will do is we will pick a value of t such that LT is strictly less than 1, right. So because LT is strictly less than 1, one can conclude that f is a contraction. So what does contraction mean? The contraction means that the distance between outputs is strictly less than the distance between the inputs. In particular, because this is less than 1, right, the distance is reduced by a factor which is strictly less than 1, right. So this is what a contractive mapping means, and this constant over here is again not dependent on the choice of y and z, right. This is independent of the choice of y and z. So what we are saying is that whatever input trajectories you give me y and z, the distance between the outputs will be strictly less than LT times the distance between y and z, that is the distance between the outputs actually shrinks relative to the distance between the inputs, right. So this is what we mean by f being a contraction. Now there is a very interesting result about contractive maps. In particular, we have something called as a fixed point theorem, which goes as follows. Suppose S is a non-empty complete metric space and f is some function which takes as input something from this metric space and spits out something in the metric space, and let us say f is a contraction, which means that f of x minus f of y is less than gamma times x minus y for some gamma which is strictly less than 1. Is this okay? So we have this condition. So if we have this condition, then we will say that we have a contraction. Then the fixed point theorem, in particular this is known as the Banach fixed point theorem, it says that whenever you have a contraction, there exists a unique fixed point x star which satisfies this condition, right. In other words, you have a fixed point of f, that is f of x star equals x star. Fixed point means that whatever you give as input, that is what comes out as output, right, and the fixed point theorem says that as long as you have a contraction, there is a unique fixed point. So we can now use this property in the context of the f that we have, right. So recall the f that we had defined, which goes from this set of continuous trajectories to this set of continuous trajectories, and we had shown that by the choice of capital T, this f is actually a contraction. Hence from the Banach fixed point theorem, one can conclude that this f has a unique fixed point. Now because it is a unique fixed point, that automatically implies that we have a unique solution to the initial value problem, right, which restricts itself to the time interval 0 to t, right. So let us go back to that initial value problem. So the initial value problem that we have been given is over here, and what we have managed to show is that if we restrict our time to lie between 0 to capital T, then this initial value problem has a unique solution thanks to this fixed point theorem. So now the question is, can we extend this solution that we have between 0 to t to beyond 0 to t interval? Okay, so the idea is very simple, right. So whatever is the value of the solution trajectory, the unique solution trajectory at time t, let us denote that as xt, right. So the initial value problem has this solution x, and whatever is the value at time t, you assign that or call that as x subscript t, right. And now you look at a different initial value problem, okay, which has the same ODE, but now the initialization is different and you look at a different time window. So earlier you were looking between 0 to capital T, now you look at the time window T to 2T, is that okay? And now one can see that a similar argument as before helps us conclude that this new IVP, okay, this new initial value problem also has a unique solution, right. Now we can stitch those two solutions. By stitch I mean that, you know, the initial solution, let us say, started at x0, okay, and at time t reached this xt, and you know the next or the subsequent solution started at xt and, you know, let us say it landed at x2t, right. You can stitch these two solutions together, right, and that would you know, lead to a unique solution, okay, for this initial value problem. So observe that in this case the initial condition is x0, but now the time window is between 0 and 2t, right. So the way we extended the solution trajectory from 0 to t to 0 to 2t was not special. So we can actually, you know, continue doing this from 0 to 2t, 0 to 3t, 0 to 4t, and in general for 0 to infinity, right. And you know, we can repeat this process also in the negative direction for negative values of t, and I encourage you to do that on your own, right. And by, you know, extending this idea both on the positive time axis and the negative time axis, one can conclude that there is a unique solution to this IVP for all t in R, right. And with that we can conclude you know, the proof of this theorem, which now guarantees that as long as your h function, which you know, can be viewed as the driving function of your ODE, right, as long as this driving function is Lipschitz continuous, your initial value problem will indeed have a unique solution. So with this, let us you know, end today's discussion. Thank you.